We'll start with actually 1D DFT, okay, and then we'll start with 1D DFT, and we want to kind of seamlessly go to really a 2D DFT. Yeah? We don't want to strain our limbs, right? So it should be like a straightforward thing, okay. Now a 1D DFT. So if you see a regular DFT, right, this is what I think your MATLAB computes, right? So it's like, suppose now I won't use V and okay, well, I'll use something like a capital F and small f, okay, just because it's a Fourier transform. I'll say capital F of k, right, that's what we normally use, is equal to summation f of n, right, e raised to minus j 2 pi by n k n. Then what is it? So the sum goes from n equal to 0 to n minus 1, and this goes from 0 to n minus 1, right? So a regular sort of a DFT is this, but then a unitary DFT, a 1D unitary DFT, 1D, right, unitary DFT, if you look at it, right, that will have a scale factor here, which is 1 by root n, summation n equals 0 to n minus 1 fn e power minus j 2 pi by n k n, okay, all else remaining the same, okay. Okay, so f of k is equal to this. Then, if you want to look at a DFT matrix phi, so the same operation, right, we would also want to think about it as a matrix vector kind of a multiplication, because as far as possible, right, we don't want to be dabbling with summations and all, right, so because when you look at matrices, then there is a lot more structure to all of this. So, right, we would want to look upon this as a vector f, okay, which is like f of 0. So this has all the coefficients of this is all these transform coefficients, f of 0, f of 1, f of n minus 1, right, this is your f, and you want to be able to express it as some matrix phi, okay, times small f. So small f is this guy, okay, is this sequence f of 0, f of 1, all the way up to f of n minus 1. So this is like n cross 1, okay, this is n cross 1, and therefore of course this guy is n cross n, right, phi, and this matrix is what we call really as a DFT matrix, okay. Now if you go back to our unitary DFT thing, right, so what we had V is equal to A times U, okay. So V we have replaced by F, U we have replaced by small f, right, and then all else remains, and then A we have of course replaced by phi now. Correct. So we are saying that if you wanted a 1D DFT, then simply replace A by phi, where this phi right consists of entries such that, okay, phi is a matrix of course, n cross n consists of entries 1 by root n e power minus j 2 pi by n k n 0 k comma n going from n minus 1, right. So if you look at it, it will have like 1 by root n, and then, and as you know, right, n varies in this manner, correct, k varies in this manner, okay. So n equal to 0 to n minus 1 as you walk along the columns, k equal to 0 to n minus 1 as you walk along the rows, because right, that's the way it is structured, no, f. So if you go down f, you have a variation of k. If you multiply phi with f, you have a variation in n, right, because a row multiplying f is like a change in n, right. So the first entries will all be 1, okay, because either k is 0 or n is 0, and then inside of course, right, you will have all kinds of e power minus j, right, whatever, depending on the size of the matrix. So these entries are typically complex, unless you take that 2 cross 2, right, like we did yesterday, that was real, but in general it is complex, right? These entries are all complex, and therefore, right, we would of course expect that similar to the case, right, that we had. So we should be able to of course invert this guy, okay, and we should be able to say that that's phi Hermitian f, okay. And it turns out that for a DFT matrix, right, because it has a certain structure, right, DFT comes like this. This is not kind of, right, any old A. I mean, this has this form. Therefore, what do you think you can say about phi transpose? Phi transpose is phi. Phi transpose is phi. Okay, and therefore you can even you don't even have to worry about the transpose sitting on this. You can simply say this phi star f. Okay, so it shows that how sort of easy it is to get on to the inverse, right? just take the original phi, take the complex conjugate, and then there you have, okay. And then the columns of phi Hermitian will now be, or whatever, phi star, right? This will be the basis now, okay. This will be the 1D basis. So these columns of same thing, right? Whatever we did for general A, all those things will hold now. So 1D, the basis vectors are all sitting as the columns of phi star or phi Hermitian, right, as you would want to call it. Now, now the point is, right, now suppose right, say until now, right, we have only, like I said, there were actually 3 points, okay. Again, kind of go back to those 3 points that I introduced in the first class on unitary transforms. The first point was trying to establish a relation between data independent transforms and dependent. Hey, by the way, a data dependent transform, right? SVD is one more thing that I forgot. KLT, I think I mentioned. SVD, right? I forgot to mention. Next day I was going to remember to tell you. I'm sure I didn't mention that. Okay, so SVD will take it up. Okay, as a sort of a dependent transform, because the SVD basis come from the image itself. Okay, so that is, I should have mentioned that. I just said KLT and I did not mention SV. The second one was about using a Kronecker thing, right, as a vehicle to go from lower to higher dimensions. The third one, right, which so until now we have kind of hovered around these two, right? We have kind of been jumping across those, but the third one, which is about, is a diagonalization, okay, which right, we haven't seen it till now. Okay, so the diagonalization has two kinds of implications, especially, right, when you're looking at actually a DFT, because the way it's some at the undergrad level, okay, when they actually teach signals and systems, right, they talk about LTI systems, and then they kind of then they would switch to Fourier series, Fourier transforms, and so on, right. So if you wondered, why that is so, right, so there's a very strong sort of a coupling between the two, right, and that coupling I thought we'll try to see that here, okay. There also I think it's fairly obvious, but here it will become even more obvious as to what this is affinity of this DFT matrix, what kind of an affinity it has for certain systems, okay, like you say LTI systems, okay. So it has a natural affinity, okay, and that affinity, that is why, in any signals and systems in a book, right, it's always like LTI systems, then Fourier, right, all the way. But here, of course, we don't want to stop with Fourier. We also want to go forward, right? Go look at other transforms. But then to sort of look at this third property, right, which we haven't examined. Okay, we'll try to make a small move towards that. Assume that right, you have a 1D system, which is of course LTI and all of that, right? 1D LTI system, and let's say right, it has an impulse response H. And imagine that, right, your input sequence is some f, and then the output is some g, right? And we know that we saw that right, we saw that that when you okay, now we saw that, right, G is equal to, so if you implement linear convolution via circular convolution, right, it said that G is equal to H times F, right? Okay, this we saw before, right? And at that time I had kind of I had sort of left it here, and I said that we'll kind of revisit later, right? So this H had a structure to it. We called it a circulant matrix, right? This had a circulant structure, correct? Now, for example, right? So if you see this as an LTI system, right, with an input and an output and an impulse response, we know that the entries of H are either 0 or it contains H in it. Correct. Correct. The matrix H, system matrix, has only zeros and a small h in it. Okay, sitting right inside it. Now the point is, right, when I want to go to the Fourier domain, okay, I know that I have my sequence G, which is in in time domain, right? Now what should I do now if I want a Fourier of this? Now we saw just now that to get to the Fourier transform, okay, we should actually multiply by a DFT matrix, okay, that sequence of an appropriate length. So what this means is that I should multiply phi with G, right? I should operate phi on G. But if I do that, and because of the fact that this is the equation that is valid, so this also means that I should multiply phi on the right. So it makes it phi HF. Okay. Now what do I do next? It still does not seem to be in a form that I would like to see it as. What should I do next? Some small trick I should play. Huh? F with how? How do I do that? But then it'll actually change that equation. No? I can't simply arbitrarily make F as phi Hermitian.
Phi G becomes capital G. Phi H, phi Hermitian will become some H delta.
Ha. Okay. Okay. I thought I didn't hear that correctly. Okay. So what he is saying is correct. So what you should do, phi H. Now we know that phi star phi is in fact identity. Correct. Phi star phi is identity, and you have F. Correct. Okay. So your equation is still balanced, right? There's no issue. Phi star phi is identity. But now what happens is, right? If you look at phi F, okay, that is F, right? That would be a DFT coefficient of the sequence F, and you are left with phi H phi star. Okay, now this should be something you see special. Okay, this should have a special affinity for H. Okay, because it's like, because you see, right, normally what would you expect, right? If you did a convolution in time domain, in the Fourier domain, it should become a product. Correct. So we have convolved kind of in time domain, we have convolved H and F, right? So on the one hand, I have here F, wherein the DFT coefficients of F are sitting. Now this phi H phi star should then do something. What do you think it should basically effectively do? Diagonalize H, correct? Which is what it does. But then, right, it does this diagonalization not because it's some arbitrary H. It is because H is a circulant matrix. Okay, a DFT has a special affinity for a circulant matrix. Okay, it doesn't mean that we can take any matrix and then do phi A, phi star, and then we will see a diagonalized A and all. Okay, that won't happen because of the fact that your H is actually a circulant matrix. Right, it turns out that if you pre-multiply by phi and then you post-multiply by phi star, then this diagonalizes H. Okay, now in order to show that, right, I'm not going to show it, right, you can actually take an example, right, write a simple MATLAB code, okay, where you can assume a certain size for phi, okay, take your H to be a circulant matrix, and then multiply that with again phi star, right. You try this. I don't want to spend time showing all of that here. I mean, this is straightforward, right? You should be able to show this. Now this suppose I indicate right, this is diagonal H. Then what this means is that I've got like G is equal to diagonal H times F, or in other words, I'll have like GK. Suppose I'm looking at the kth coefficient, that is diagonal H KK FK. Okay, so if you look at this diagonal entries, right, of this diagonal, it will be all 0, and just that you will have like diagonal H 0, 0, diagonal H 1, 1, all the way up to n minus 1, n minus 1. Okay, that will be that matrix. So naturally, right, this should be something. No, this can't be. One is, of course, it is the eigenvalue of H, correct. But then more than that, it has a relation with small h. What is that? It is in fact the DFT coefficient of H. So for example, I mean, if I because I've used a capital H already here, suppose I had written suppose I computed DFT of H. Are you following this? I mean, right, because I can show this. I mean, you want me to show this, then then it will be okay. Now you know what, I can take actually a 3x3 example, right, which is what I was searching for, right, whether I have, see, for example, okay, I'll just maybe, okay, right, I'll just show you. Suppose you had like an example, okay, a 3x3 example, then okay, the way it will look like is phi H phi star, okay, will look like 1 by 3, okay, 1 1 1. You can go and verify this. 1 e power minus j 2 pi by 3 e power minus j 4 pi by 3, then this will be 1, this will be e power minus j 4 pi by 3, this will be e raised to minus j 8 pi by 3, right. and then you will have your circulant guy H0, H1, H2, H2, H0, H1, then H1, H2, H0, and then you will have phi star, okay, which is 1, 1, 1, 1, 1, then Ej 2 pi by 3, Ej 4 pi by 3, Ej 4 pi by 3, and Ej 8 pi by 3. Okay, so if you actually multiply this, right, so this diagonal matrix that you get, okay, you can show that if you say expand this, right, then each of these diagonal entries is but the say DFT. So the first entry will be the 0th DFT coefficient of H. The second is that is diagonal H1 comma 1 is like, is like the first not first, the second DFT coefficient. So H of 0, H of 1, H of 2, right, if you think about it, till H of n minus 1. So each of these is but the DFT coefficient of small h, which is what it has to be. It can't be anything else, right, because you are doing a product, you are doing a convolution in time domain, that has to give you a product in the Fourier domain. But you see, normally, right, we don't see it in this form. In a matrix form, we don't see it often, right. We tend to write integrals and so on, and then that's how we see. But then it's nice to see that in a kind of a matrix vector form, right. It's nice to see the circulant matrix coming in, the DFT matrix coming in action, right, with respect to a circulant matrix. Okay, now you can also show that, so for example, right, I mean, so to show that, okay, these are the eigenvalues and what are the eigenvectors, right. So what we can do is, so we have diagonal H, right, is phi H, phi Hermitian strictly speaking, but let's say call it as phi star now. Then it means that if I want H, right, then I should multiply by on the left by phi Hermitian, this guy, and then on the left I should multiply, phi star, no, I don't know why am I writing, phi star delta H phi, right. So that is equal to H, correct. So now suppose let's say, suppose I call phi I star, suppose is the ith column, of phi star, this matrix. Okay, suppose it is the ith column, then you can see, right, what will happen if I act H on phi I star, then that's the same as phi star diagonal H phi, and then this vector phi I star. Okay, phi and all is a matrix, phi I star is a vector, and because we know that phi star is identity, therefore when you multiply every row of phi with phi I star, right, what will happen? So you will get all zeros except one in the ith entry, right. So this will be like phi star diagonal H, and then you will get a vector which will be like 0 0 0, and then in the ith place, right, because the ith row of phi, when it multiplies phi I star, okay, that is when you will get a 1 here. So this is like the ith what is that, ith place, ith entry, and then again 0. Now since you have a diagonal matrix here, right, so what will this be equal to? Phi star, again all zeros, except that here you will get, what will you get? One entry you will have to make, no? What will that entry be? Delta H is diagonal, no? Delta H I comma I, right? Diagonal, I mean, so calling it, or you want to call it lambda, whatever you want to call it, delta H I comma I, and then 0. And okay, and then this we know is the same as 0 times the first column of phi star plus 0 times the second column plus plus plus. But then delta H I comma I times the ith column of phi I star. So this is delta H I comma I phi I star. Okay, so you see that H phi I star is some scalar times phi I star, right? So which means that the columns of phi star, not phi. Okay, the columns of phi star are the right eigenvectors of H, and the corresponding eigenvalues are given by, and the corresponding eigenvalues are are in delta H, right? Delta H I comma I, and so on. Yeah, but this is a kind of a fairly obvious thing, but still I just thought I'll show this. Okay, we are still in 1D. Okay, now if you go further, right? So one way to look at this, the action of right, this is the third property. Okay, third property where I said that we look at this diagonalization. And if you go back and see, right, I said that diagonalization both from a system point of view as well as a data decorrelation point of view. Okay, there were actually two things that I had mentioned. So a system point of view is this. Okay, for at least a DFT, because of the fact that Fourier transform, right, has this convolution product kind of a nice relationship. Not all transforms have it. Okay, now the other one, okay, which is a common thing in fact across transforms, that is what is called a statistical point of view. So I would rather call this as really a system point of view, right? So this diagonalization, okay, is from really a system point of view. This diagonalization that we saw just now, it is from a system point of view. From a system point of view, right? But the next thing, right, that we will see is really diagonalization from a statistical point of view. Statistical in the sense that a data, the covariance and so on, a statistical point of view. So from a statistical point of view, right, it is actually interesting that if I have a covariance matrix R, right, if I have a covariance matrix R, okay, which is circulant, and of course, right, if you ask when does it happen, if you have a periodic random sequence, right, that will have R as circulant, and in fact many times, right, a Toeplitz matrix itself, right, one can show that asymptotically, right, a circulant and Toeplitz look the same. As the size begins to become larger and larger. So in that sense, making a circulant assumption even for a Toeplitz is okay for large dimensions. Okay, so if you have a covariance matrix which is actually circulant, but then when you look at covariance, right, then it brings in more structure. See, if you saw the H matrix, right, that we had earlier, H, for example, we said it is circulant, but then it need not be symmetric and all, no. Right, you can have a Toeplitz matrix, but then, right, there is no guarantee that it should be symmetric. Okay, which is why when you look at the coefficients, right, of when you diagonalize, you can get entries which are actually complex. Which is why we say that the DFT coefficients are in general complex, right? We don't expect them to be real. But when you talk about a covariance matrix R, right, this is not the same as really a system matrix. Now, this is a covariance of some data, right? So how do you calculate that? Let us say that, right, when I give you lots of examples. Okay, one way to estimate is so you sort of, right, take the average of okay, if you let's say if you dissolve zero mean, then you will do xi transpose, right, and sum it over all the examples, right? That's how you will estimate covariance, right? Because many a time you have data, but then you will have to estimate the covariance, right? Nobody directly gives you an analytical R, but if you have an analytical R also, it's fine. Sometimes R is analytical also. If it is not, then you learn it from the data, whatever it is. But then when you have a covariance matrix, right, it automatically, because of the way it comes, right, a symmetry is automatically there, right? Look at the fact that expectation XX, right, XX transpose already means that right, symmetry is there. Okay, which then means that if you now try, because like I said, right, a DFT matrix has a special affinity for circulant, but then it doesn't care whether that circulant is coming out of a system matrix or somewhere else. Okay, so now if I try R, suppose I do phi R phi star, the same operation that I did there I did it on H. Now instead of H, which is from a system point of view, now I come and look at a data covariance matrix R, and suppose I try the same stuff, right, phi R phi star, then what happens? This will diagonalize R. Okay, like I said, no, as long as it is circulant, it will kind of say diagonalize it. But this diagonalization has now a big implication. Because now, right, it's like saying that if R has a strong correlation, right, if R is a matrix, suppose, for example, right, if R is not diagonal, okay, you've got lots of off diagonal entries, that means there is correlation. Now this guy, when you take such a matrix and then if you try to do this operation, this will actually decorrelate the data. Decorrelation, and this is something that we will see when we do KL transform. It simply means that it is reorienting, right, from your standard basis to another basis, right, in which right, things look. So it's like saying that if you had a standard basis, right, like right, these are your x and y, right, these are your standard basis, but then suppose I had some data like that, right, very kind of closely, right, something like that. Now as I increase x, right, I mean I can see that y is also increasing. Okay, so it means that there is a correlation which is strong, right. I mean, this is supposed to be slightly noisy. Okay, this is not exactly on this line, some are below, some are above, something like that, right. It's kind of a noisy data, right, which is around a line. Now if you're going to think about this line, right, it looks like as x increases, y is also increasing. That means there's a correlation. So if you compute a covariance matrix for this, that will show up in R. That correlation will show up in R. But now if you say that instead of this axis, suppose I take one of the axis to be this and the other axis to be that, right, suddenly you see a decorrelation, because now it looks like even if I don't transmit the one, right, which is now, so for example, if you look at the variance is very high along this, but then the variance along the other, this one direction of this data is very small. So you might say that I might capture most of the information by just sending this and not even sending that, which may not be exact and all. What error you incur in a mean square sense, that we'll see later. But I'm saying, right, so this decorrelation is about all this. So instead of a standard basis, right, you kind of reorient, with respect to some other basis, and typically it's your eigenvectors. That's where your KL transform, PCA and all come in, because the best basis that you can have, right, that will decorrelate is in fact your eigenvectors for that R, right, and therefore, right, so here the implication is something else. Here it's not about DFT and all of that, right. Here it's not about convolution or anything. It is about taking a covariance R, and if you had a covariance R that is circulant, then you could apply. Now what normally happens is, right, sometimes if you had a choice, let's say I had DFT, I had DCT and all of this, right, I have all of this, then what can happen is, right, it may happen that, okay, it may so happen that none of them is able to kind of say diagonalize. Suppose I have some R, okay, whatever be it, okay, I'm not assuming it is circulant. Okay, if it is circulant, right, so here is where Sabare said that, right, that there could be a bridge between a data independent and actually a dependent transform. So right, this is one such case where a data independent transform diagonalizes R, okay, without in a sense that in a sort of a perfect sense, okay, a perfect sense. So in that sense, right, this is now the optimal transform, even though this is data independent, right, because this phi basis is coming from nowhere, right, we have already fixed it. But if R turns out to be circulant, then the best transform that you can use to decorrelate data is in fact a DFT, and in fact DFT is in fact the KLT. Okay, so that bridge that I said, right, there could be bridges between data independent and data dependent transform. That comes about in this case, but sometimes what may happen is none of them may be able to diagonalize it exactly. In the sense that after you do this operation, you may not get really a diagonal R. You may still have a few things left here and there. Okay, if that happens, then you might want to ask which transform should I then use, right, for that kind of R. Okay, so which is the reason why the statistical part, right, is more involved. The convolution part is only for LTI, and then DFT is the best, and then we stop there. But then when you talk about data decorrelation, which is the third point, that diagonalizability, that has more implications, okay, because anytime you have data, right, because it's all about data, right. Today look at the outside world, everybody talks about data analytics, data mining, data, it's all data, right. So if you construct covariance matrices out of all that data, and if you want to make effective sense out of them, then all these guys, right, are sitting out there, right, and then people, what they do is effectively try to find out which one works the best and so on. But this is a very simplistic thing, right. What they do is far more complex. But I'm just saying, right, if you just stop at second order, right, in the sense that if you stop at covariance, which is like a second order statistics, if you just stop there, which means that you're sort of you're assuming that there's Gaussian right, underlying law is simply a Gaussian, may not be true, right. There may be higher order statistics and all of that. But if you just stop there and you say that, right, I treat all my data strictly Gaussian, then, right, R is all that you have, right. You're going to see sufficient statistics is basically mean and R. So with that, right, with that this diagonalization property, okay, then it starts to assume importance, and then you start worrying about which transform is best to use and so on. Okay, in this case, turns out that this will be a perfect diagonalization, and this is what we mean by really a decorrelation, data decorrelation, still in 1D. Okay, now the move to actually 2D, right, is very straightforward. Okay, we don't have to do much. A 2D DFT. Now, if you ask, right, and then if you know how to do a 2D DFT, then a 3D DFT, a 10D DFT is all fine. Okay, a 2D DFT, what will we do? We'll just go by whatever we did. So we will say, if I had an image, right, suppose I call that as f, okay, f of m comma n, and then if I want to compute my DFT coefficients, 2D DFT, from now on I'll call this as unitary, right, automatically. I'll assume that I'm talking about unitary DFTs only. Okay, and then suppose you call that as, what is that? So f, a capital F of m comma n. Okay, then it means that in order to compute a 2D DFT of this, all that I'll do is what you can all kind of write this down now. F is equal to, so for example, right, if it is square, and suppose this is of size n cross n, then you will simply take a capital phi times f, where f is n square by 1, this f is n square by 1, and all these coefficients which are your transform coefficients are all sitting as, so for example, if you look at the first entry, right, that will be like 0 comma 0, okay, and then f of 0 comma 1, then 0 comma n minus 1, then 1 comma 0, all the way. Okay, they're all sitting in this n square by 1 sort of a vector. And this phi, right, and please note that I put it like sort of a capital kind of phi, right. I'm not writing it. It's a 1D DFT. I wrote it like that. A 2D DFT, right. I want you to be able to separate the two. So I'm writing it as like this. So what is this guy? This has to come as phi. Then you take Kronecker with phi. So whereas this phi is n cross n, this phi is n cross n with the corresponding to 1D. And then you do this Kronecker, this will give you a phi which is n square by n square, because we know, and that is what will multiply this f. Okay, straightforward, right, in one shot. Now, if instead of f of m comma, if let's say if this was actually a rectangular image, what would you do? If this was n cross m, what would you do? Oh yeah, m cross m, sorry, m cross m, not m cross n. N cross m, see, this is the point is, right. So for example, if you had a 2D image, instead of a 2D, if I had a video, let's say, right, if I had some k number of frames, right, then if you kind of look at this whole 3D object, what will that be? That be like m cross n cross k, correct? Now if you wanted a 3D sort of a DFT, what would you do now? You would extend it as what? Phi. You would add one more, simply a Kronecker, which will be phi k cross k, right. So this guy will actually multiply, now u will be what size? M into n into k by 1. So right, you will have to convert this whole thing into one vector, right, one long vector, right. You may not implement it like this, right, nobody implements like this, but then this is just that insight, right, that going from a lower dimension to a say higher dimension, it's just straightforward, right. You just which is why I said that a Kronecker product, right, is the guy that kind of sits, and then now you can imagine if you go to a 4th dimension, and whatever, right, it should all make sense. One simply doesn't take it just for the heck of it. But if it makes sense to have a 4-dimensional object, right, whose Fourier transform you want to take, 4D DFT, right, then again, okay, you can do all of that.